This is the first of our videos on complex numbers, and this is from the AS1 module of CCA A-Level Further Maths. Okay, complex number. What is a complex number? We've got the quadratic formula for quadratic equation. So we have x is equal to minus b plus or minus b square root of b squared minus 4ac all over 2a. Now, this part here, b squared minus 4ac, we've talked about this down the school as being called the discriminant. And if the discriminant is negative, what we should have said is that there are no real solutions. So a complex number is where you persist with the idea that you can have a square root of a negative. And the square root of a negative number gives you what's called an imaginary number. So a complex number, so basically what complex numbers are all about is you have the square root of minus 1. Somebody persisted with the idea that you could have the square root of a negative, and square root of minus 1 we call I, and this is an imaginary number. So a complex number generally would be in the form like 4 plus 3i. So the 4 is the real part, and the 3i is the imaginary part. Okay, and that's it basically. So you've got a real part and an imaginary part, which makes up a whole complex number. So sometimes it will just have the imaginary part, that's because it's completely imaginary, but if for it to be a complex number, it has to have both of these. Okay, we're going to look, go through the notes here. I'm going to skip past this bit. You can read through this bit in your own time in the notes. We're going to skip past and jump on to the first example and see how we add and subtract, add, multiply, and divide complex numbers. So here we've got 4 nice easy examples to get us started. The first one, it says, simplify each of the following, giving your answers in the form a plus bi. So remember, a is the real part and b is the real part, and a and b are real numbers, so that's all it means here. So like they're positive or negative real numbers for your a and your b. Okay, the first one is just adding 2 plus 5i plus 7 plus 3i. So you've got two complex numbers here. 2 plus 5i is a complex number, 7 plus 3i is a complex number, and we're adding it. So to add these, all you do is add the real parts. So the real parts are 2 and 7. 2 plus 7 is just 9. And add the imaginary parts. The imaginary parts are 5i plus 3i, which is just going to be 8i. So very, very easy indeed. Okay, for part B, we're subtracting. So I'm just going to write this one out. It's just a wee bit trickier just with the subtraction. So I'm just going to write this out getting rid of the brackets. So it's going to be minus 5 and then minus 11i, which is going to be plus 11i. So that's the only reason I wrote that out. And then you have got the real parts are 2, then minus 5, which becomes minus 3. And the imaginary parts are minus 5i plus 11i, which is going to be plus 6i. Okay, the next thing we're doing is we're multiplying. And when this isn't multiplying by a complex number, this is multiplying a real number by a complex number. So it's just 2 upon 5 minus 8i. And when you do that, 2 times its 5 gives you 10. 2 times the minus 8i gives you minus 16i. Okay, and what we're doing again, we're not dividing by a complex number. We're going to see that's a little bit more difficult. We're dividing by a real number. So everything here is divisible by 2. The 10 divided by 2 gives you 5. 6i divided by 2 gives you 3i. And that's it done. Okay, it says here, solve the equation z squared plus 9 is equal to 0. So, oh, sorry, what's happened there? So what we're going to do here is we're going to just say z squared, rearrange, is equal to minus 9. Now, if you were in this situation before, you would have said there's no solutions to this because you can't have the square root of a negative number, and you're absolutely right. There's no real solution of a negative number, but we're going to persist with the idea that there is. Okay, so z squared would be equal to plus or minus the square root of minus 9, and we're going to split this up, this minus 9, using your rules of surds. I'm going to write that minus 9 is the same as 9 times minus 1. And remember, this is what complex numbers are all about. The square root of minus 1 is equal to I, which is an imaginary number. So that's going to be equal to plus or minus, square root of 9 is 3, and the square root of the minus 1 is I, so plus or minus I, and that's it. This next example, if you got this, you could try and factorize and try and work it that way, but it's because it's complex, I've had a fair idea it's not going to work. So I'm going to jump to my quadratic formula. So z is equal to minus 6 plus or minus bracket 6 squared minus my 4ac, so 4 times the 1 times the 25, and it's the square root of this whole thing, all divided by 2a, which is just 2 in this case. Okay, that is a mess. So if something's a mess, you tidy it up. So on your calculator, just do 6 squared minus 4 times 1 times 25, and that gives you minus 64. So they've been very nice to us here. It's all divided by 2. So just on this, folks, had you been in this stage previously, you would have said there are no real solutions, but that hasn't changed. Not that we were lying to you down the school. That was always the case. There are no real solutions. So here, but there are imaginary solutions. So this is where we're going to have, it differs a wee bit. So minus 6 plus or minus, and we're going to write our minus 64 as the square root of 64 times the square root of minus 1, all divided by 2. Another couple of lines here just. So that's going to be minus 6 plus or minus. Square root of 64 we know is 8. The square root of minus 1 is I, all divided by 2. And then if you can, if the numbers are nice and you can divide by 2, do so. So it's going to be minus 3 plus or minus 4i. Okay, we're now going to look at multiplying complex numbers. Now remember we said that I is equal to the square root of minus 1. That means I squared equals minus 1. So we're going to use that in this example here. So here we've got A, and A is equal to 2 plus 3i, and that's upon 4 plus 5i. So do this whatever way you want. You use FOIL. You may use FOIL. I use the curly lines just. So 2 times 4 gives me 8, and 2 times the 5i gives me 10i. Nothing difficult so far. 3i times 4 is going to give me 12i. And then this is where it gets tricky. 3 times the 5 gives me 15. I times I gives me I squared. Okay, tidy up whatever you can. You've got 8 plus 22i. So the middle two terms can be grouped together. And then you've got 15 times I squared. I squared is now minus 1. And then you've got 8 plus 22i. 15 times minus 1 is minus 15. Tidy up again. That's going to be minus 7 plus 22i. And that's it. Okay, so there's a couple of wee steps in here. Clearly, you could have, when you get a wee bit better at these, you can skip out steps here and just jump from here. You'd say that that's 8 minus 15, which would be minus 7, and this one you could group together to be 22i, but I've just shown all my steps here. Okay, part B, we have got 7 minus 4i all squared. So I'm just going to write that as 7 minus 4i upon 7 minus 4i. So it's good to take this easy step here just to avoid making silly mistakes. 7 times 7 is 49. 7 times the minus 4i is going to be minus 28i. Minus 4i times the 7 is going to be minus 28i. And then we've got minus 4 times minus 4, which is going to be plus 16 times I squared. So tidy it up again. That's going to be 49 minus, and that's going to be 56i. And then that's going to be minus 16. And tidies up to be 33 minus 56i. Okay, complex conjugate. We're going to see why this it's very important for complex numbers in many ways, but we're going to see one way very soon. But for any complex number z, which is equal to a plus bi, the complex conjugate of the number is z with wee star, and then a minus bi. So basically, you change the sign of this second thing, and that's it. Right, so, and again, together, z and z star would be called a complex conjugate pair. And we'll see when we're going on later on, we'll see about roots of complex numbers, and we'll see why complex conjugates are important. Roots of complex equations, I should say, complex polynomials. Complex conjugates are very important. But also, as we'll see in a wee minute, when we're dividing by complex numbers, why complex conjugate is very important. Okay, we're going to look at use these in this first example just. And see what happens. Okay, so first thing we've got is our z is equal to 2 minus 7i, and part A of this says write down the complex conjugate. So complex conjugate is just z plus 7i. It doesn't look like a 7. So z 2 plus 7i, I should say. Part B says find the value of z plus its complex conjugate. So if you just do that out, that's just going to be 2 minus 7i plus 2 plus 7i. So if you add those, what you just get, the imaginary bits cancel out and you just get 4. So it's completely real. There's no, the complex number plus its complex conjugate just gives you a completely real number. Okay, next thing, it's asking me for z times z star. So I'm just going to write that out. That's going to be 2 minus 7i upon 2 plus 7i. Now hopefully we see that this is a difference of two squares. So it's going to be 4 minus 7 squared, which is 49, times I squared, which is going to be 49. I squared, remember, is minus 1, so that's minus 49 times minus 1. So 4 plus 49, which is going to be 53. Okay, note the modulus of a complex number is denoted by modulus of z, where modulus z is equal to a squared plus b squared. So it's a bit like the length, the modulus of a vector, the magnitude of a vector, same idea. So your modulus is equal to square root of a squared plus b squared. So for example, the modulus of z in this case is going to be 2 squared plus minus 7 squared, which would work out to be 53. So it's the same as a squared plus b squared. So here, and it's the same as, then your modulus of z is exactly the same as modulus of z squared is the same as z times the complex number z star. Okay, dividing complex numbers. To divide complex numbers, what you have to do is you multiply both the numerator and denominator by the complex conjugate of the denominator. So this really, folks, doing this, it is really a bit like rationalizing the denominator of a surd. So that's what I'm going to just show you at the side here. If you had 2 over 1 plus root 3, how you would rationalize that, you would say 2 over 1 plus root 3 times, and top and bottom get multiplied by 1 minus root 3. That's how you would go about doing it. So it's a very similar idea when you're doing complex dividing by complex numbers. So in this example, it says, write 5 plus 4i over 2 minus 3i in the form a plus bi. So basically, it means it's getting they want you to divide this thing. So write it out. It's 5 plus 4i over 2 minus 3i. What you want to do is multiply top and bottom by the complex number of the denominator, which is 2 plus 3i. Okay, if you do that out, what you're going to get, let's do one big line here. 5 times 2 is 10. 5 times the 3 is 15i. 4i times 2 is going to be 8i. And then 4 times the 3 is 12. I times I is minus 1. So 12 times minus 1 is minus 12. So this is the first time I've skipped the working out for that bit. Then in this one, this is a difference of two squares on the bottom line. So it's going to be 4 and then minus 9 times I squared, which is going to be minus 9. I'll show them working out for that one. Minus 9 times minus 1. And then we'll go up here. So top line becomes minus 2. And then that's going to be plus 23i. And your bottom line is going to be 13. And that's it done. So technically they wanted us to have it in the form a plus ib. So it's going to be minus 2 over 13 plus 23 over 13i. And that's it. Okay. Last wee note for this video, nothing else for you to write, but it says two complex numbers are equal if and only their real and imaginary parts are separately equal. So if z1, complex number 1, and z2, complex number 2 are equal, therefore x1 plus I y1, that's the real part of z1 plus the imaginary part of z1, is equal to x2 plus I y2. So if you bring both those, the real bits all to one side, you're going to have x1 minus x2. If you bring the imaginary parts all to one side, you're going to have I upon y2 minus I upon y1, and they've just taken the I outside of brackets. And then what they're doing is just squaring both sides. Now, the reason they're squaring both sides is just to get rid of the i's in this. So Square both sides. You'll have x1 minus x2 all squared is equal to minus 1 upon y2 minus y1 all squared. And then bring it all to one side. You're going to have x1 minus x2 all squared plus y2 minus y1 all squared is equal to 0. So you have something squared plus something else squared is equal to 0, and that's very important. So since this thing is squared, it has to be positive. Since this thing is squared, it has to be positive as well. So it's not like they can cancel each other out. So that means this thing has to be equal to 0, and this thing also has to be equal to 0. So x1 minus x2 has to be equal to 0, and the only way that can happen is if x1 is equal to x2, and this thing is equal to 0, and the only way that can happen is if y1 is equal to y2. So the result is if their two things are equal, then their real parts are equal and their imaginary parts are equal. Now I think that's quite a tricky proof in a way, because to me that just seems so obvious, and if something's obvious it's really harder to prove. But there you go. And the last thing then is your 0 number, I suppose. If x plus iy is equal to 0, then the x bit is the real bit 0 and the imaginary bit is 0. Okay, folks, from your complex number question booklet, you can do these questions, or if you've got the textbook, it's a P3 book, page 116, exercise 7a, and there's a long list of questions for you to do.